This is going to be on non-equilibrium. So let me start with something which is equilibrium. I want you to look at these two videos. So this is basically the first video of Brownian motion taken by Jean Perrin. So here you have colloidal particles executing Brownian motion in a confined space. So this is the first video. Have a look at it. And this is the second one. So one of the videos is running forward in time and the other is running backward in time. So can you tell just by looking at the videos which one is which? The answer is no. You cannot tell this for any macroscopic system because this is a feature of thermal equilibrium, the central feature of thermal equilibrium, that there is no notion of time. You understand thermal equilibrium in terms of thermodynamics when you look at just macroscopic systems in terms of the average quantities, average macroscopic quantities, pressure, volume, temperature, whatever. And if you are looking at fluctuations of those quantities, you are basically doing equilibrium statistical physics. So you do not need time, there you go forward in time, backward in time, you have time reversal symmetry. Cut to non-equilibrium systems, this is exactly what you break, and this is how at the basic level you would like to understand non-equilibrium. Again, let me play you two videos. These are basically, this is a herd of wild beasts moving through a Serengeti National Park. You see this video, and if I just show you this video, it's very clear which one is forward in time and which one is backward in time. So time explicitly plays a role in non-equilibrium systems, and for the rest of the talk, you will see that I will come back to time again and again. So how do we classify non-equilibrium problems in general? There are various ways of looking at non-equilibrium. The simplest way to look at non-equilibrium is by looking at this in terms of some external drive that acts on the system. So you can think of some global drive, for example, some kind of potential difference, chemical potential difference, or just electric potential difference, or some kind of advective velocity that advects some kind of a die, or let's say some kind of scalar fields. So the point is, the easiest way of looking at non-equilibrium systems is by looking at macroscopic flows through the system. Now there could be another class of non-equilibrium systems where you don't apply a global drive, but you just look at the individual entities that make up this macroscopic system. So these entities intrinsically have some way of converting the energy from that they get from their surroundings into some kind of mechanical motion and dissipate the rest. Now to sustain these kind of states, you need to continually feed them energy, and this drives them out of equilibrium. For example, the first picture that I show you is that of clusters formed by genus particles. These genus particles are coated on one side by certain kind of dyes. If you shine light on them, they behave in a persistent manner. If you bring a lot of them together, they form these clusters. If you turn the light off, they will start doing Brownian motion. The second one is a picture of flocking, which is very famous, basically the thing that gave birth to this active matter, this branch of active matter physics. So these birds, one can see them at very simple minimal level in terms of these microscopic spins, which interestingly have some kind of self-propelling drive. Now when you bring these birds together, these birds look at their neighbors, align themselves with some kind of noise with their neighbors, and they start to generate this kind of macroscopic flow patterns. If you turn off their self-drive, then these things again disappear and you have just Brownian motion. And the third example, which I will get into much later in the talk, is basically that of pulsating cells. So you have cells which can change their size and shape, and you bring a lot of them together. This happens in tissues, and you see that this kind of you have this kind of emergent phenomena of waves, density waves propagating through the tissue. And there could be one other class of non-equilibrium systems, and these are not exhaustive sets, but then you can have systems where you don't do any driving to the system, but the system's internal landscape, the free energy landscape, is such that it can get trapped in any local minima, and it can take an enormous amount of time to go and access its global minima. So in these cases, what you really look for are relaxation properties of these systems, and typical example are glassy systems. So I will mainly be focusing on the first two kind of things today. Also I'll get into this kind of memory effects in a moment, but let me just first tell you what are the questions of interest when I look into non-equilibrium problems. So first of all, what are the steady state properties of these systems? These are not equilibrium steady states. These are steady states, but inherently non-equilibrium. So what sort of non-equilibrium signatures can I draw? Where do these signatures hide? They usually hide in phase transitions. They give you phases which have no equilibrium analog. And once you see these phase transitions, you would like to figure out how to analytically or even numerically find where these phase transitions are in the system, and in many cases you basically have to look at large fluctuations. At the typical level, many times these phases don't even show up. Then there are these questions of relaxation properties. So you start with some initial condition and the system may or may not relax to a final equilibrium or non-equilibrium state, and you are only interested in the transient properties, and I will explain these kind of problems in a moment. So what is really important in this kind of questions is what is the role of memory. So if you start the system with some initial state, how long will the system remember its initial state, and how does the initial state affect the dynamical properties of these complex systems? Yes.
It's a function of time window which you need the observation, right?
Yes.
The type of simulations. These simulations, they're very difficult for us to say whether we are stuck in a local minima or a global minima because of the time that you actually make the observation.
Yes.
So, maybe you will say this in your talk. Is there a way a priori to know the kind of work you do? How does one predict if this non-equilibrium will crop up, it won't, or is it really a matter of time? Are there ways to answer these questions?
So, I mean, there are different levels at which you see molecular systems, either at the microscopic level or the macroscopic level. Sometimes you can just be looking at a macroscopic system, and even if you start with some kind of non-equilibrium dynamics, the features of non-equilibrium might completely hide in the macroscopic features. So you have to really understand the system at a base level, microscopic level, and then ask this question basically, do you see these signatures at the hydro level? So I'll show you examples of these kind of things. So that's basically the answer. Yeah.
Just a quick comment. So you can also have an equilibrium time versus symmetry breaking. Right, that's allowed. Like if you put a system in a magnetic field, that breaks time reversal, but it's still an equilibrium.
Yeah, but putting it in a magnetic field, I mean, you're still driving the system.
But I can look at like the long, let's say I'm at a constant magnetic field.
Of course. But a system, an isolated system left to itself, will execute properties of time reversal symmetry. I didn't say the term isolated. I mean, you just won't make it interact with anything. Just leave it by itself. If you just look at the macroscopic behavior of the system, if it's in equilibrium, however you bring it to equilibrium, if it is in the equilibrium state, then time reversal will be there.
That's the part I don't understand. So let's say you are in a system with charged particles in a magnetic field.
Yeah.
And you look at long term.
Yeah.
Then you can have steady state chiral current.
But that's your flow. Your flow in the system.
Yes.
If you have flows in the system, then you have actually gone out of this time reversal domain.
But it's still an equilibrium in the sense that it's.
But I would not call it, because if you are driving the system and you have a microscopic flow, let's say call it the way you prepare that state is basically an equilibrium state.
Even like if just to start this condition, you had to put in some current. I'm looking at a system, let's say charged particles in a magnetic field at very long times. They just.
But if you have a circular flow in the system, I would not call it an equilibrium system. But it's a matter of whether you want to call it or not.
So there's a current in the system.
There's a current in the
conductor put in a potential difference the same.
Yes, I mean,
But if you have a circular current, it doesn't carry current, right? It's in a magnetic field, so it goes around only. It's not propagating the current.
yes, I mean, there's
It's
also
in a closed loop.
so yes, and then again when you talk of equilibrium, it's again a matter of which one you want to call equilibrium or not. I mean, so it's a very debatable question sometimes as well, but yeah. Then it will relax. Then it will relax to state where there is no circulating current anymore. So, but I will see the magnetic field as an external influence on the system. So it's just, yeah. Yes.
So it leads to some non-equilibriums system. So
Yes.
so if we consider active matter, so the drive is from inside.
Yes.
So that also non-equilibrium.
So again, I mean, in active matter systems, even if you have sometimes microscopically breaking this time reversal symmetry because of this internal driving of the systems, at the macro level, you may or may not have a non-equilibrium picture. For example, this motility-induced phase separation has a well-defined equilibrium picture, but it is made up of all interacting agents which are non-equilibrium themselves. So it's these questions, and there is no one answer to these questions. So there are varying answers. Let's say. Anything else? Okay. And of course, the last point was basically if you have a global versus a local drive, what sort of phenomenology do you see emerging in the system? And these are basically different things when you apply a drive globally instead of applying drives locally. So these are basically the questions of interest broadly on this. So I will move into some examples now of non-equilibrium systems in 1D, and then I will go into 2D. So let's look at the 1D systems first and why these systems have been of my interest for some time. So, thing that we look into, that we looked into for the last 3-4 years, not last, before that, because I've been looking into the systems. So, we are looking at a very peculiar thing in a way that the initial conditions are remembered by certain systems in 1D. So, the statement of this problem is basically that if you look at certain complex constraint systems which have diffusive dynamics, which is made up of entities which execute diffusive dynamics, then the transient behavior for this wide class of diffusive systems basically show an everlasting dependence on the initial conditions. They are never really forgotten if you consider infinite systems. Now, this kind of systems have been studied for quite some time. I mean, the earliest paper that I could find was basically by Satyam Majumdar and Mustansir Burma from 1991. Now, in this class of problems, there are essentially two sources of randomness. One that comes from the microscopic dynamics of the individual entities, and the other comes from the how you have initialized your system, from the initialization protocol. Now, what are the examples of these kind of systems? So, for example, think of this problem of effusion. You have a pipeline which carries some kind of gas, there is a hole in the pipeline and the gas leaks out. Now, in this question, what you are really interested in is the current of the gas that is flowing out of the pipeline. You are not really interested in any steady state property after the gas is leaking out, right? So, this is a transient problem inherently. So, you would like to understand these kind of questions in terms of fluctuations of a current. Now, you could study this in 2D, 3D, anything, but it's easiest to study in one dimension. It's already quite complicated, but we can gain a lot of insights. So, how do you make a one-dimensional model of these kind of systems? So, you say that all particles live on some kind of a semi-infinite line. You distribute particles from 0 to L and take L to infinity, and then at time t equal to 0, you switch on the dynamics, and you see how many currents have basically crossed the origin up to time t. So, this is a very standard problem of non-equilibrium physics. Why is this particularly interesting? And this is basically Derrida's contribution in this class of problems, where he picked out that the role of initial conditions is identical to the role of disorders in disordered systems. So, if you are not motivated fully by this kind of examples to do non-equilibrium, let me give you a more concrete example which is relevant in case of life. So, here I am showing you an example of single file motion. So, what is single file motion? So, you take a bunch of particles on the line, you just let the particles move in between the spaces of their neighbors in some kind of random diffusive manner, but no particles are allowed to cross each other. Why is this particularly interesting? Because this happens in our cell membranes. So, what happens is, so this is basically the age of biosensors. So, this is kind of biomedical engineering that is going on. So, this is also very old. I mean, this is 2008. So, this red one is one kind of a protein. It's basically GPCR. Let's not get into what this protein is. So, the functionality of this protein is such that if a ligand comes and attaches to this red protein, it changes its structural organization. If this red one is coupled to this ion channel, which is the blue protein here, then the ion channel opens. And once the ion channel opens, these ions can get into the tissues or the membranes or the cells in single file motion. This term single file motion was actually coined by Hodgkin in the year 1955, and it has remained a classic problem of non-equilibrium physics for a very long time. Now, what are you interested in when you are studying this problem? You are really interested in the dynamics or the displacement of one tagged particle. You want to understand, to follow how this one tagged particle in this set of all diffusing particles or interacting diffusing particles is moving around. Yes.
This one particular one, you did not talk about the interaction. You just
Okay,
said
so
that the particles and that they cannot cross and they're not interacting.
Okay, so the only interaction, let's care about only one kind of interaction where it is hardcore, so they are not really
So
going.
if it is hardcore, then if the density is a little bit high, then the particle can only jiggle in the space between two particles.
Yes.
And it may not give. Okay, I mean, we were talking about the mean square displacement of the tagged particle.
Yes. I mean, there is a very standard dependence on density in this case. It basically goes down as 1 over density, the displacement.
Something
So
like that,
the
yeah.
displacement, I mean,
Yes.
we are talking about the variance
Yeah.
and the mean, these things. So what is interesting in these classes of problems? You see, these are seemingly very different problems, but there is a big universality hiding in this class of problems. So when it comes to initial conditions, so again I repeat, so in both these classes of problems, there are two sources of randomness. One is how you initialize the system, and the other comes from the dynamics. So when it comes to initialization of this kind of these systems, then there are two ways that people have looked at initializing these systems. One, again, this is the idea of disordered systems, when you fix the initial profile and just average over the dynamics to look at the macroscopy, to calculate the moments and distribution functions of the observables. So either fix the initial profile and average only over the dynamics, or for every realization of your experiment, you let the initial condition fluctuate as well. And then you average over both the initial condition and the dynamics. So this way of looking at this kind of initialization problems is called annealing. Now, if you take these two approaches, what one sees is that the dynamical fluctuations from these observables, the current, the mean square displacement, these are all dynamical observables. What you see is that the dynamical fluctuations of these observables, they always remember the initial state. What does it mean? So if I take, for example, on the left, you have the variance of the position of a tracer particle. If you take the annealed average and take the quenched average, then you see that they are both scaling as square root t. At the level of scaling, they are the same, but the curves are off by a certain factor, a numerical factor. It's basically square root 2, and it's a very universal number. Then if you just look at the same problem in terms of the current, then again you see there is this square root t dependence of the dynamical fluctuations, but these lines are off by a factor of square root 2. Now there is a vast literature on this, very vast, but it was a rather incomplete picture, because ideally you would like to understand what is special about these two lines, and why do these two lines always show up? Is there one framework that actually captures the whole role of initial conditions in these problems?
But these kind of systems are weakly interacting systems.
So these are all interacting by hardcore exclusions. When it comes to current, you can either have a non-interacting system or an interacting system. They are equivalent, because when it comes to density, all that matters is the density.
But usually in strongly interacting systems, these systems forget about the initial conditions as well as the dynamics.
Yes, even here, if you apply a length scale to the problem, and I'll talk about it, I mean, there is a dependence on the large length scale density fluctuations that show up. If you fix the length scale, then there is a length, if you fix the total length, within a certain length scale, you will also forget about the initial conditions. But you see, there are some systems, as I showed, this one, there is no length scale to apply, it's a transient problem. So these are questions of fundamental interest in some sense. So basically the challenge was to come up with a general physical mechanism. In these cases, how are initial conditions remembered in these classes of 1D problems, and what we are able to achieve. I'll not go through the maths, I'll just show you the main results here. So if you look at the variance of the current or the variance of the displacement, the way initial conditions enter the problem is identical, and the entire effect of the initial conditions at the level of typical fluctuations can be encoded in a single number, which is this red guy, this alpha IC that I mentioned. Now this bunch of universal results, they apply to a wide class of diffusive systems. So for example, we arrived at these results by solving a microscopic theory as well as a macroscopic theory. Without getting into the details, this is universal, and the most important part is whatever problem you are looking at, the dependence of the initial state is hiding in one number. Now, what is this number? And this is what the physics really hides. And it's important because now I'll tell you something here. So if you are looking at this alpha is nothing but the structure factor of the initial state. Now, if you are looking at the long time regime, this structure factor is dominated by the wave number going to 0. So this is basically telling you that it is only the large scale fluctuations which go and affect the dynamical behavior in the long time limit. What is this alpha? So this alpha, the structure factor, basically measures how much fluctuation you have in the initial state, how much density fluctuation. If alpha IC is 0, then you basically have hyper-uniform initial states, which means the initial state is completely ordered. If you have fluctuations, these fluctuations are not scaling with the system size. And this is an important insight, because when I talked about quenching in the first place, quenching, you see, people talk about quenching in terms of the initial state not fluctuating. What we are saying here is you can let the initial state fluctuate, it doesn't matter as long as the fluctuations are small. Now, you can tune alpha continuously from 0 to 1, 1 being the fully randomized initial condition, which people have been calling as annealed initial condition. You can interpolate between them continuously, so there is an infinite family of curves which you can understand completely in terms of this one number. And that's the physics of this problem. And what is more important is that sometimes we only look at scalings in these kind of systems, or in any system for that matter. Scalings don't tell you everything. A lot of physics might hide in numbers as well, in the coefficients, and this is a problem, a simple problem that brings this out. So this is one of the works, and it really opens up a lot of interesting questions that you can ask. So this gives you a new way of looking at this relaxation phenomena. So for example, you prepare an initial state, and the problem of the current actually goes beyond 1D. So you prepare an initial state, look at the current, and information of the initial state will be hiding in the dynamical fluctuations. Then you ask these questions of aging, because you see there is this insight of disorders in this problem, and how long have you waited before you took your measurement. That waiting time will show up in all the calculations, in all the results. Then you go and ask these questions of anisotropy. You go beyond 1D, give x and y as different drifts on x and y, and you see what effects you get in those systems. What happens when you have shapes of these particles? So instead of considering point particles, if these are extended particles, shapes will come and play a role, and we have to understand what these things do. And of course, a later time goal would be to build more of a hydrodynamic framework for active matter systems, when these particles are not just diffusive. For diffusive systems, we have this macroscopic fluctuation theory, which we solve to understand these things. If you have active matter, we do not know if there is one hydrodynamic theory or different classes of hydrodynamic theories, and if this gives you a framework to study these things in simple settings. Yes.
So I can remember what is a new framework, in the sense, suppose I'm looking at a class problem where people look at aging and look at mean square deviation and see at different waiting times. So there is a standard protocol in the typical simulations where people study this.
Yes.
Suppose if I were to take this framework and try to, how should I think about that problem differently? What is new about it?
No, so I mean, if you are trying to understand glass with this, no, the insight is you now bring insights from glass and understand electron process in this kind of 1D settings or 2D settings. But you can, the idea is you can look at dynamical fluctuations in glassy systems, let's say, and that can reveal information about the structure factor of the initial state. This is already known. For glassy systems, no, but the idea that you can really take the waiting time, and that waiting time shows up in these kinds of problems, that is a new way of understanding these systems. Because these problems of current fluctuations and pressure, these are important. They don't necessarily have to relate to glassy systems, but there is an insight that you can draw. So if you want more insight from glassy systems in these problems, in physics, just study different branches of physics. So
No, I'm not talking about that big picture. I'm saying a very practical matter, in the sense that one of the questions I'm glasses, what people want to know is that, is this going to be a glass former? Is it a glass former or not? Suppose if I'm trying to understand for that kind of questions,
yes.
I don't already know, is this a glass former or not? Maybe that information that it's a glass former may be hiding somewhere. I'm trying to understand, is this methodology that you're suggesting, is this one way of thinking and looking at certain fluctuations, where some information can come which I may not get in a normal way. I'm trying to understand how to connect this.
It could be, because for example, in this class of systems, we do see signatures of snow drifts, aging, and also caging for that matter. So it's a question of, I work on this kind of problems. So for me, I have to then go and talk to a glassy, someone working in the glassy community, to then bridge the gap and see what insights can you draw from here and apply it directly to glasses. But there are many signatures of glasses that show up in these one-dimensional settings, and importantly, they show up when you have active systems interacting with each other. So there are many of this caging and snow, as I said, and we found this in a different paper. I mean, so you have to connect these things together.
Just a quick question, sir. On this plot on the right, the point is that this black line goes through well around the round circles, but not through the red one. What is actually the difference?
Okay. This black one and red one are two different hypervolume states. The black one is basically when you have equispace initial condition, and the red one is some fluctuation around the equispace, but it is still preserving the hyperuniform structure. Now, this I think is a finite system size effect. If I have many more particles, I think I use here something like 5,000 particles. If I have more particles, then you see the exact matching between them.
So that is supposed to goes to infinity.
Yes.
And this alpha IC also will depend on system size, and because not only the initial conditions but also the system size.
So you see, I mean, alpha IC is defined in this infinite system size limit when it's a structure factor for t going to 0. Now, you can define, first you can define a system size and create numerically engineered systems which give you a certain alpha. So my answer is you can take a, I mean, when you do the simulations, you only have finite system size, right?
Settings, that's what I wanted to understand.
Yes.
So with finite size, right?
Yes, of course. I mean, the point is when you do these simulations, you have finite size and you create different alphas in finite size. So you can, I mean, there is a way of putting in this L directly in the equation for alpha. Right. There is a way to do that. Yes, of course. Yes.
When you discuss about this hydrodynamic framework, usually hydrodynamic equations have fixed points, and you have some dynamical equation here, balance equation something. And do these fixed points match, or how do you know that whether it will have a eventual?
So it depends on, I mean, when you say fixed points, I mean, there is a steady state or something, in relaxation problems, there is a steady state. So there is a fixed point as such. So when you're doing theory framework using this case, you don't have to look at a fixed point. I mean, you have well-defined framework, you just see whether the predictions that you get, for example, from the hydrodynamics, you map it with a microscopic system. So in terms of hydrodynamics, you have hydrodynamic parameters, which are written in terms of the microscopic parameters. So you take a microscopic system, simulate, and you see, this is what we did here.
So usually when you have hydrodynamic equations,
fixed points. So for this problem, you don't have, and for the next problem, you will get about fixed points. But you see, this is the thing. I mean, so if you have hydrodynamic theories, it can, I mean, if a hydrodynamic theory can encapsulate a lot of different microscopic processes. For example, this, the first figure here for the displacement, this was obtained by solving a hydrodynamic theory. It's called microscopic fluctuation theory, but it encaptures various kinds of diffusive processes, Brownian motion, dynamic process, and simulation process. All of them are formed by the same hydrodynamic theory. And that is the notion of universality that you see in this class of things. Yeah, so this is statistical. Yes, I mean, you see, you're looking at the initial state, and you don't care about relate to the initial state. Just look, you start from a state, it's just a static problem that you care about. Okay, so now move on to non-nuclear extensions in 2D. So I think they already have questions from 1D. If you have still questions, feel free to ask me now, because now there is a shift of dimensions now. So let's. Okay, so this picture that I showed you, so this is what that we put on a trade. So this is, we'll talk about how we get to this kind of pictures. So just to give you a brief idea of what this is telling you that you start from some linear state, you create instabilities, and with instabilities you eventually go and form waves. We'll see what we mean by this kind of system, what sort of pictures we have in mind. The first picture that I show you here is that of the amniotic, it's a time series map of the amniotic fluid pressure inside the human uterus during the first stages of labor. So, and you see that this amniotic pressure, it shows you oscillations, which are basically signatures of contractile waves that propagate in the uterus. The second picture that I show you is a schematic of the human heart. Now, in the human heart, you have basically the sinoatrial node, which has pacemaker cells. It throws out waves that propagate through the heart. Now, if you have a normally functioning heart, if you look at the ECG of a normally functioning heart, then this contractile behavior shows up in these PQST beats. These are well-defined PQST beats. But now, if you are unlucky, if you have tachycardia, for example, then these beats become irregular. And if you are more unlucky, then these irregular beats transition into called ventricular fibrillation, which is a precursor of cardiac arrest. Now, if you probe these things in terms of the voltage action potential, which the heart cells actually experience, or if you just probe the calcium ion concentration, then you see that these stages are actually associated with, so for example, the tachycardiac phase is associated with reentrant spiral waves, and when you look at basically these ventricular fibrillation, the spiral waves transition to what is a state of defect turbulence. Now, what do I mean by this kind of waves? Let me show you a video of this. So when you are in, this is basically a map from tachycardiac heart to a heart with ventricular fibrillation. It's the same heart. An experiment done in Georgia Tech. So you see, you first started with the spiraling waves, then the pacemaker comes in here and it breaks out the spiral wave, and when you are transitioning towards a ventricular fibrillation from well defined spirals, you are basically seeing this emergence of defect turbulence. Now, okay. So ideally, I am not really trying to understand what the human heart does or what just the uterus does. Contractile wave propagation in human tissues or any animal tissues is a very generic feature. So, we are trying to understand through a minimal model how do these waves come about. So, what could be the minimal ingredients to build up such a theory? The first thing that one has to note, if a tissue is composed of cells, if the tissue has to contract and expand as a whole, then the individual cells must contract and expand. So, this is the first thing that one has to keep in mind. The second thing is cells are essentially localized in very dense environments. So, you do not need to consider self advection of these cells. So, these are still active systems because these cells can change their shape and size, but they are not really moving large distances. So, you do not care about advection. Now, in a dense system, it is obvious to expect that the cells, they live in a confluent system, right, because there is no empty space in tissues. They should affect each other's pulsation. So, one cell cannot just pulsate individually, it should look at its neighbors and then pulsate. And you need a constant supply of energy. This is living matter, this is non-equilibrium matter. So, you need to supply constant source of energy to carry out the dynamics. So, these are the minimal physical ingredients that you need to build such a theory. Now, these insights were used by Etienne Fodor and Yue Zhang, people in our group, to write down a microscopic model for this kind of systems. So, what they took was a bunch of repulsive disks which were able to synchronize. So, you have 2 degrees of freedom. One is their position and the other is their phase. This phase is basically a measure of the size of the particles. Now, given the size, the particles interact with each other in terms of a repulsive potential, which is U. Okay. The insight that they drew from this was that when you actually bring a lot of them together, you look in your phase space, you play with density and the synchronization, which is this. So, particles can synchronize their size by looking at the neighboring particles. So, if you do that, then you get these various kinds of waves propagating in the system. So, you could have planar waves, you could have circular waves, or okay, sorry, it's the same thing. Or you can have these rotating spiral waves, and if you increase the density further, you have these defect turbulent waves. Yes. Yes, of course. No, okay. Let me slow down. We are in a continuum. Every particle can be mapped by its position and its size. There are 2 degrees of freedom. The position is controlled by a potential, which is this U. Okay. This U in turn depends on the size of the particles. The dependence of the size is encoded in psi. Psi has a dynamics. There is a drive that pulsates the particles that allows this psi to evolve and which leads to this pulsation. Okay. And then there is also this U, which is basically the repulsive potential that it feels, and there is a synchronization term, which is something like a Kuromoto synchronization term, which the particles feel, they look at each other and try to make its own size equivalent to the size of the others. Okay. And we add a bit of stochasticity just because real systems are stochastic. Okay. And these guys, I mean this mu and mu psi, and the way Etienne handled this model, they imposed fluctuation dissipation relation that you just cannot have arbitrary mu and mu psi, because in the limit of this drive going to 0 and synchronization going to 0, you should expect the system to follow equilibrium dynamics. Okay. So, this is basically the model. Sigma is the size of the particle, the radius. Yes, yeah. And lambda is basically controlling how much it can expand and shrink. Is the model clear now? Okay. I am not going through the microscopics too much because I am talking about hydrodynamics. And what Etienne was able to do, he took this microscopic model, he coarse-grained it, but he neglected density fluctuations, but he arrived at equation of a density. And so you see, this is a many body system. You have many particles. From here, If you want to understand things analytically, you have to coarse grain this system. So what they did, they coarse grained it. They arrived at dynamics of two fields. One is a density and the other is a complex field which is an amplitude and a phase. Okay. Interestingly, what they were able to find was that this maps onto this equation of this phase maps onto a complex Ginzburg-Landau picture with a symmetry breaking term. And this symmetry breaking term, this C actually depends on the macroscopic potential that you have, and this breaks a continuous gauge invariance. And if you break that, you end up with this hydrodynamically, you end up with these states of motile defects in the system. But this was an incomplete study in the sense that you cannot really expect density fluctuations to vanish even if you have a dense system, because in real life systems you see density waves. There are experiments which show you density waves. So phase cannot just change and the density remains constant. So what we had in mind was to really make a continuum theory, because these continuum theories are good to look at and easy to understand. When I say good to look at, they allow you a lot of analytical tractability in them. So how do we build continuum models? So first of all, the reason for building a continuum model again is the universal appeal. If you build a hydrodynamic theory, there is a lot of microscopic system which can come into this hydrodynamic theory. Of course, bring in density fluctuations because you would like to replicate what the experiments do, and like in any other system, these are systems which can be replicated on the tabletop. So we would like to have a control on this system. So we would like to understand what the phase picture is, so understand the phase diagram of this system. So let me give you an idea of what we have in mind here when I am making this hydrodynamic theory. So let us say every individual cells, they can pulsate with a certain drive, and the size is encoded, I mean the information of the size is encoded in the phase of each individual cells. Okay. Now these undergo some kind of cyclic oscillation, so different values of the phase will correspond to different size of the particles. You bring a lot of them together, you make a confluent system. So there is no empty space, which is a schematic shown here. You would like to describe this in terms of not individual entities, but in terms of a field, a coarse grained field which depends on the position. Now the mechanics of this entire system is encoded in the density field and the phase field. And if you want to look at this same picture in terms of a continuum picture, then you would look at this in terms of a phase field and a density field, and this is a rough representation of the same thing, where you have basically a low density means smaller particles would correspond to a lower density. That's how you should read these kind of maps. Any questions so far on this? Yes, I mean in Nathaniel's model those are disks. This is a schematic because no, yeah, of course. So the microscopic model, there is a question of confluency in this problem. Yes, but in this setup that I am drawing now, you assume there is a confluence. There is confluency.
It's just a question. Why do you call this phase?
It's an oscillating system. There is a size that oscillates. You can, the phase is equivalent to the size, so it's all the same. You can call it the size, but it is not the size. Psi is a measure of the size, and I will show you how. So it maps onto the size, but it has the same information.
So where is it being encoded, whether it is confluent or non-confluent?
In the next slide. So how do we build that? So we are trying to build a theory for pulsating liquids. So how do we build a continuum model for this? So let's look at the physical assumptions. So first assume that there are no cell death or cell birth. So number of particles is conserved. So you have an equation of continuity for the density, rho will be the density. Now you say that given this system, there is a target reference area which the cells will try to achieve. For that, the inverse of that area will give you a reference density. So if the cells remain at that density, then all the elastic stresses vanish. Which means the moment you deviate locally from this elastic density, you create an isotropic stress in the problem. You could have an isotropic stress as well, but let's say you build an isotropic stress. Now you say that the tissue lives on a surface essentially, so this gives you friction, and then you can use stress balance to get rid of the velocity and write down the equation of density purely in terms of free energy. Now this free energy is just considered in terms of a compressibility, which is lambda, and you see this rho minus rho f basically gives you a measure of the displacements that particles can have. Now where is this confluency coming in? It is coming in through the form of rho ref and the elastic free energy. So this epsilon which is this guy that controls the magnitude of pulsation, this couples density and phase. So now if I write down, so basically the next question is how do I write down the dynamics of psi, and it will be clear now when you have the full equations, density and phase, they are both giving you a they give you a set of coupled equations. So one cannot go without the other. So this is where you are going. So how do you really write down the dynamics for psi? So again you see what do we have at the moment? We till now there is no non-equilibrium in the system, right? Everything is controlled by a free energy. So now you, as I said, the cells would like to reach a target area. So if there are spatial gradients in the cell size, that will incur some kind of energetic cost. So the free energy that we write down is basically the elastic free energy plus a gradient term. Now this is all equilibrium. So at this level, the only non-equilibrium that we put in is by a drive that acts on the phase. There is nothing non-equilibrium about the dynamics of the free energy, but you see through this free energy these two fields are coupled, and this is where the idea of confluency comes in and sets in this problem. And you see if I now just drop the free energy altogether, because of this omega you will still see pulsation, right. And just to go back one slide, why do I choose this form of rho ref? Because it's a phenomenological model. So it's a phenomenological idea that we want the tissue to oscillate. So if if the system is such that it's in a global synchronized state, then the tissue would oscillate, or even individual cells, when they reach this target area, they should oscillate. And if I keep on driving my system, because of this cosine term, they will just keep oscillating in their size. This is the physical motivation or a phenomenological motivation for writing this kind of terms. Alright, so I have given you enough maths for this system without getting into too much of it. We do solve this theory, and what are the results? So let me go slow on this. The phenomenology of this model is there are three states essentially. One, so I have various control parameters. So in this problem we look at two control parameters, one which is like the inverse of the drive, let us say the drive itself, and the total density which is conserved. Now in terms of these control parameters, I see there are three phases. One, when for a given density, if you have sufficiently strong driving in the system, then you can have the states of global cycles. Now global cycle means all the cells are doing this oscillation in a synchronized manner. So they are all contracting and shrinking together. If for a given drive the density is very high for a given drive, because it's a competition between the two, then these mechanical interactions can actually stop the pulsation from happening, and you end up in this arrested state. This is a dynamically non-changing state, so there is nothing going on. So you can understand this in terms of basically a fixed point of the hydrodynamics. Now this green line that you see in this figure, so just look at one figure for the moment. This green line that you see gives you the transition point between a transition line between a homogeneous arrested state and a homogeneous cycling state. That is when you have no perturbations in the system, no noise in the system. Yeah. I'll come to it. Yes, there are. So, and we are trying to characterize it. So once you have this green line, then you would like to understand what sort of instabilities can you have in this system. So you have two homogeneous states here, homogeneous cycles and homogeneous arrest. So you look for you do a stability analysis of both these states, and then you find out that there are two regions, one where the cycling states become unstable and the other where the arrested states become unstable, and then you probe what is going on. In the next slide I will show you the patterns. Yes. Cycles are basically globally oscillating states. So now if we look into these regimes, for example, if I look into the state where look into the region of the phase space where the arrested state is destabilized, what I get, I'll come to again how do we check this numerically in terms of some model parameters, but let me show you first what we are seeing here. Yes.
So can you comment what might happen if you also take into account the dead birth process?
That is what I am working on now. I can tell you what happens. Let me show you the patterns. The patterns don't change, the phase boundaries change, and some interesting things happen in terms of what are the control parameters there in the system, because there is a new time scale. So things change.
How do you get the phase boundaries?
How do I get? Okay. I kept them as backup slides. Let me see again. So you see, if I non-dimensionalize my system, I write down my because it's a macroscopic 3D, I need to know what are the length scale and time scales. If I do that, then I can write down the dynamics in terms of some effective landscape, right. This is not a free energy because there is no like ground, like no final minimum of this thing. But if I still cheat a bit, if I still say that okay, this is like something like a free energy and analyze the structure of this guy F, which is basically this quantity, you have this beta and I mean this is basically rho, and you study it for different rho star values, then you see it's a competition between the drive, which is this minus I, and this free energy, let's say. So now as you change, for example, this is for different values of beta for a given value of rho star, let's say total density, then what happens is you transition from a state of multiple minima to a state where there are no minima, and this you can analyze by just looking at the shape of F. So, you look at the fixed points and other things, and when you have this minima, the system can get trapped in this minima. This is arrest. The reverse is basically the cycles. So, this is how we see. Of course, I mean, but the question is how do you define these things is a more non-trivial question, because these are inherent non-equilibrium states. So, it's always entropy being produced, but again to characterize them is a bit, yeah. And basically this is the green line that is there. So, you just look at these two things and green line, and after that you can actually ask how does space affect stability, which will give you these two lines, the red one and the black line. This is how you, and you do linear stability analysis to get this red line, standard linear stability analysis. When it comes to cycling states, it's much more non-trivial. What we did was a Fluke analysis, because you have time periodic coefficients, and we are able to get these lines, which, I mean, linear stability was already very good to capture the phase behavior. Okay, so let me go back. So, what are the patterns basically? Not this. So, if I look at an arrested state, so I start with, let's say I start with a homogeneous density, homogeneous phase, but it's not fully homogeneous, the phase. I give very small perturbations to a homogeneous state, okay, and I want to see how this emerges, how this physical system emerges. And if I just play the movie, so you see, you start from a homogeneous state, there are domains that form, and then these domains undergo a secondary instability, and you get to this phase of waves. Once you hit the state of waves, these are stable, the waves are always there, the waves don't go away. So, it's a non-equilibrium system, there is no equilibrium analog of this. So, if I played the movie backward, you would see the waves go back in, that doesn't happen, right. So, one could ask what happens when you destabilize cycling states. So, you see the colors are changing, but again it's the same mechanism, it's a spinodal instability, okay, it's a bit odd, okay, let me see if I have the video here. Yes. So, you see the state is basically for cycling, and then again these local domains are developing, and then once the domains develop, they undergo a secondary instability and you have the waves. There is a difference between these two kinds of patterns. You see the secondary instability that I am talking about is different in each of these cases. So, for the first case, when you have these waves coming from the arrested state, you first hit a Turing instability, which is what you get when you have spatial fluctuations in the system, and then you create these domains, and within these domains you hit a Hopf instability that gives you these waves. In the other case, in the cycles, you hit a Hopf instability first, you see the entire, there is no time translation invariance in this problem, you hit a Hopf instability, but still these domains form, and then you get these waves. Yeah, this is a, check that, it is just exponential.
And then the secondary ones means the nonlinear effects.
Yes, yes. So, the waves are not captured by linear stability. They only give you this spinodal instability and the length scale of the patterns. So, if you freeze the system and study the length scale, you will see that linear stability is correctly giving you the pattern length scale, but then the secondary one is nonlinear. So, these are nonlinear waves.
And then the later times, what do you get if you evolve?
Yes. So, if you don't have any, so these are big systems, first of all, these are 100 systems with fine grid size of 0.25. So, if you wait for a very long time, ideally, if you take small systems, then this inside is clear. If you have multiple pacemakers which are throwing out waves, what really matters is which is the dominant pacemaker. So, they will come, they will converge, and you have only one pacemaker. If you have a big system, in the thermodynamic limit, there are many of these pacemakers, and I waited for very long time in terms of time, what we define as time in this case. I didn't see all of them merge, but there are some cases where I can see them merging for sure. But then we want to understand this in the presence of dynamical noise. When there is dynamical noise, there is heterogeneity and there is no one pacemaker. We have these multiple pacemakers which are throwing out these waves. And this is the question we asked. So, if you have dynamical fluctuations, can you still understand the system analytically? Numerically, of course, we first looked at the system, we looked at the phase diagram. So, what we saw was that the patterns qualitatively do not change. So, noise, I mean, it's something that is seen in repeated problems of noise in this kind of pattern forming systems, that noise hardly changes the patterns of the system. What it can do importantly is change the order of transition. There are these models of this flocking based models where people actually show that if you do hydrodynamics with noise and without noise, you either get a second order transition or a first order transition. Here we always simulated with noise, and the only thing that I saw when I looked at my order parameters was that it changed continuously. It could be sharp, but it still changed continuously. I will still not make a final comment on the order of transition because I have to do a proper system size scaling to really come up with whether it's second order or first order transition, and also looking at what sort of coexistence we have. In this model, it seems like at the moment we are seeing a second order transition between phases because it's spinodal.
So, but it may not be.
It may not be, yes, but
The crossover.
it could be crossover because I have not calculated the exponents. So this is why I don't want to make this comment. It seems very continuous at the moment. But okay, so what are these order parameters?
The noise is of a particular kind, like you always use.
Sure.
So does it make a difference if you use like 1 over f first?
Could be. I am not sure at the moment. At the moment this is all Gaussian. Why? Because we just wanted to put all non-equilibrium into this drive. Because if this drive is not there, this d rho and d psi, they are chosen in a manner that they satisfy fluctuation distribution. They are not arbitrarily chosen. So just wanted to see if there is only one source of equilibrium, how different the phenomenology is from equilibrium. So okay, just to bring some technicality into this discussion, the order parameters that we checked the system through was the first one was basically this Kuromoto order parameter. So it measures the homogeneity of the system. So if the system is homogeneous, which it is in terms of arrest and cycles, then R is basically 1. And if you are in a state of patterns, then R deviates from 1, and it can be anything between 0 and 1. But that doesn't really differentiate between an arrest and a cycle. For that, you have to measure the phase current, how much the phase changes in a certain amount of time in the steady state, and then you see that basically these are again in non-dimensional units. So this phase current is basically close to 1 when you have cycles because it's driven completely by the frequency, and if you're in the arrested state, there is no phase current, it's stuck. So phase is there, and if you subtract out the homogeneous contribution from the phase current, you see that the phase diagram that you get from the synchronization parameter and the phase current, they match, they overlap. So these are the kind of numerical tests that we did to verify the analytical phase diagrams. Okay. So the point again that I want to make, if we checked the role of dynamical fluctuations, and what we showed that the dynamical fluctuation, the patterns are not changed by the introduction of noise, but what is important is that noise comes and shifts the phase boundaries. So there are regions, for example, you see in this region all these lines are coming very close to each other. What noise can do is expand this region, and this is what we found analytically using some kind of a small noise expansion, and of course we tried to verify this numerically. This works better for small values of the noise amplitude because the analytics is done for a small noise expansion. All right. So let me give you some perspectives of what can be done in this kind of hydrodynamic theories of pulsating matter. So first of all, this is a minimal field theory. So we took the minimal ingredients and we have arrived at this formation of waves in these systems. Interestingly, these waves are not just phase waves and no density waves. We have synchronized waves of density and phase. If you have waves in phase, you have waves in density and vice versa. So what are the open questions? The first thing is basically what is the order of transitions? Is it first order, second order? How do we really characterize that? If you are in an ordered phase, is it a truly long range ordered phase, or is it a quasi long range order, or is it some kind of an order? So we have already seen that noise can come and destabilize ordered phases. So it's a matter of being more quantitative and understanding these kind of questions. Then what is the role of anisotropy in this problem? If you have viscosity, you have shear, how do these patterns change? what is the role of cell division and death? Basically, cell division, cell death, I mean, if you don't conserve the number of particles, then what changes basically is that you don't have a spinodal instability anymore in this system, but you have a finite Q instability still. So, you still have the patterns, it is the same kind of patterns, but now the phase diagram changes because you have new phase parameters coming in, new time scales coming in. What is the role of invading species? So, if you have a different density field which is now interacting with these pulsating tissues, does pulsation come and stop the flow of these invading species, or does pulsation aid it, or what is the interplay between these two things? Because, I mean, I have in mind some kind of tumorous tissues, but these are the questions one will ask, and then a later goal is to understand what is the role of structure in these problems. You go from pulsating liquids to pulsating solids, you do not write the equation in terms of a density, but in terms of displacement fields, and then you try to understand what sort of interplay you have between structural defects and phase defects. What sort of waves do you get in that case, what sort of patterns do you get, and how does one affect the other. And then a much later time goal, or maybe not later time goal in terms of optimal control, but for pulsating matter, how do you control these systems such that when you go from one point in the phase diagram to other, you minimize the least amount of heat. So, there is a framework that I like to use for this kind of questions. It is a framework developed by David Sivak and Gavin Crooks. It is very interesting in the sense that they look at a thermodynamic state space and say that you can, if you have perturbations which are weak and slow, then you can use ideas of linear response to write down a friction tensor which endows the thermodynamic space with a Riemannian geometry. So, the minimizing of your heat in these kind of systems essentially boils down to calculating geodesics of that friction tensor. And I am talking about, today I have been talking only about pulsating media, but it belongs to a broader class of deformable particles. So, if you are interested what is the future of deformable particles, I will point you to this very 1-year-old article, PRL viewpoint on this kind of deformable particles, what sort of features you can look at, what sort of questions you should ask, one can ask, one can try to answer, and where the field is headed. So, just point to this one, which is just quite a good job in my opinion. And before I end, I just thank all my collaborators, because all these 1D problems, 2D problems, whatever I have learned is because of very patient collaborators that I had with me throughout my life. And basically, yeah, that's it. Thank you.